Dear Reginasailing family and friends and all others who want to learn a little bit more about celestial navigation. So far we have come quite a bit. We have come into the 17th century. The century until the seamen just used to determine their latitude. So that's perfect. So we can sail down to a certain latitude, go west and wait until we find the Caribbean. And in modern times we can switch on our radio, and if we hear salsa we have come too far south, if we hear jazz we have come too far north, so if we hear reggae music then we are on the correct latitude. That's how they did. Now to get the longitude we have to understand one theoretical principle. It's going to be very difficult to grasp maybe. My goal is that you just flip through and listen through what the background is, how you can pre-calculate the altitude of a celestial body and the direction of the same, the azimuth, on many places on this earth. And then you compile it in a book which is called the Sight Reduction Table. So you don't need to follow all the individual steps later, but try to understand the background. And when you've said, I now get it, how you can do this, then we can start using the tables to determine our full position in our next chapter. But follow me on the theory course here now first.
So what we've done before is that we have understood that we can measure the distance between us and the sun somewhere on the earth. We can calculate the zenith distance. So the zenith distance is easily found by taking 90 degrees minus the observed altitude. The sun moves along its declination, and in the afternoon you have another zenith distance, the zenith distance 2, which is 90 degrees minus the second observed altitude. We get two position lines, and where these position lines cross, that's our position. That's the principle. And now the beauty comes, namely that we have some pre-calculated angles at known positions. So how does that work? How can you pre-calculate the angle that you should be measuring at a certain position? Again, we have our boat, we have our star, and we have the zenith distance in between us. Now, what's different now is that let's assume that we know our position. So we have our latitude and have our longitude, and now we want to calculate at our position which would be the angle we need to see in the sextant. So by doing that, it's best to know the position of the sun as well. And we have found out that the declination, the latitude of the sun, we can find out. We found it roughly in the Reed's Almanac. We found it precisely in the daily page, on the daily pages of the Nautical Almanac. Now the sun moves along this line, and the question is, what is its longitude? For that reason we need a reference line. Well, the reference line for the declination is the equator, and the reference line for the longitude of our position is Greenich. The longitude of the sun is also calculated from Greenich. So we'll take this Greenich line, and that is called the meridian. It has 0 degrees, and the position of the sun is thus the declination, which corresponds to the latitude, and then something called Greenwich hour angle, GHA, of the sun, which corresponds to the longitude. So the difference between a longitude and a Greenwich hour angle is very minor. And I honestly think that I prefer the Greenwich hour angle to the longitude, because the longitude has the problem that it has east longitudes and west longitudes, and that is just pure historic. One wanted to know how far am I from home, from Greenwich, from London, in longitude east or west. And by the way, the charts in the French chart had Paris and I'm sure the Swedish charts had Stockholm as their meridian. But since the British ruled the world, I believe that that's the reason why the British charts have taken overhand everywhere, so you use Greenwich as the meridian. The practical thing with the Greenwich hour angle is that it has no east or west longitude. It starts off at 0 degrees at Greenwich, and then just like the longitude, 10, 20, 30, 40, 50 degrees west, and at 180 degrees west, which is on the other side of the world, it continues 190, 200, 210, 220 degrees, all the way around to 360 degrees. So the Greenwich hour angle is a number between 0 and 360 degrees. So we have the position of the sun. Well, we have the declination, but what is the Greenwich hour angle? You can almost guess it. We can find it on the daily pages of the Nautical Almanac. So again, the Greenwich hour angle is found on the daily pages on the 21st of September in our example at 9 o'clock. We can see that the Greenwich hour angle is 316 degrees and 44.7 minutes west, so to speak, always west. So, and this is on the hourly angle, on the full hour. If you go one line below and look at 10 o'clock or 11 o'clock, you will see how fast the sun moves in east-west direction. So you can't interpolate. You really have to do this more precisely. So you look first at the full hour. So on the 21st of September, you look at 9 o'clock. That's why I have marked it with a big 9. And what we really want to get the knowledge of is the Greenwich hour angle at 9 o'clock, 34 minutes and 12 seconds. So how much did it pass on between 9 o'clock and 9 o'clock and 34 minutes and 12 seconds? Well, not quite to 10 o'clock, but somewhere in the middle. So for that reason, you looked at the increments. That is on the back of the book of the Nautical Almanac. We look at that page. Here it is. You can look at 34 minutes. That's the 44 minutes page. Then you go down in the first column to 12 seconds. And you find out that the sun and planets actually have moved on 8 degrees and 33.0 minutes. So these two figures we have to add, and then we know exactly what is the Greenwich hour angle of the sun. So when we've done that, we go back to our picture. We know what the declination is and what the Greenwich hour angle is of our celestial body on the Earth, the sun in this case. So let's zoom in and look a little bit closer on what we have here. We have the zenith distance. What we want to do is we want to pre-calculate the angle on the sextant that we should measure on our position. The calculated angle HC is 90 degrees minus zenith distance, because that we know from beforehand. So if we know the zenith distance, we just need to do 90 degrees minus the zenith distance, and then we get the calculated angle HC. So what we really want to know is the zenith distance, this yellow line. Okay, let's look more what we can find on this little nice Earth surface. We have the declination, and by knowing that the North Pole is straight up, it's latitude 90 degrees, then we know that this part here, this angle, is 90 degrees minus declination. The same thing or a similar thing is valid for our position. So our position has a latitude, I have marked it here, that is a known figure. So since we know the latitude, we know this line, which is 90 minus latitude. So now we have a nice little triangle, but we need some more, namely an angle. Look at this. Can you recognize that the angle between the red line and our longitude is the angle of longitude? So this angle between the red line and the white line is our longitude. Further, we know that the angle between the red line and the blue line is the Greenwich hour angle. So the difference between longitude and the Greenwich hour angle is the angle between the white line and the blue line. I mark it here in green. This is an angle called local hour angle, or LHA. And the local hour angle is our longitude minus the Greenwich hour angle. So if we now take away all the other lines we don't need anymore, we have a nice triangle now, as I said, with two known sides. The blue side is 90 degrees minus declination, and declination is known, found in the nautical almanac. Then we have the white line, which is 90 degrees minus latitude, the latitude we know. And in this triangle, we have a green angle which is known, which is the local hour angle, which is nothing else but our own longitude, which is known, and the Greenwich hour angle, which is known from the nautical almanac. And this is the very famous PZX triangle, which so many people do not understand. And I hope maybe you have a little bit an understanding for what this is, because the beauty of this is that if this had been on a flat paper and we have a triangle where we know two sides and an angle, we can calculate by means of the sinus formula and some other mathematical tools which are taught in 10th grade in school. Then you can exactly calculate all the other angles and all the other sides. And since this is on a sphere on the Earth, it's not quite as straightforward as in 10th grade. You need to do a little bit more triangular calculations, into which I will not dive here. I will just give you the answer. But you can maybe understand that if we know two sides and an angle, we can know all sides. And what we want to know is the zenith distance. So these are the magic formulas. You don't need to know these. You just need to see that the HC can be calculated if you take the arc sinus of cosinus, your latitude, and multiply it with cosinus, your declination, and multiply it by cosinus, the local hour angle, and then plus minus sinus latitude times sinus declination. And Zn is the azimuth, the direction to the sun, is arc sinus of sinus local hour angle times cosinus, declination, and so on. So if you know these two formulas, you can put them into a little pocket calculator, and then you can make a lot of money, or you could make a lot of money by selling these for a Texas Instruments calculator. These are readily known. They are very old, these formulas, and in the olden days you needed to use these to calculate by means of logarithm tables, but these days it's much easier. Because if you can calculate it for this position that we have here, you could calculate it for every position, right? So at each position on the Earth, we could calculate an angle which we should be able to read of the sextant. So if we are here and the sun is there and we have a certain time, because you need a time to read off when the sun, where the sun is, so the declination and the Greenwich hour angle of the sun, you could easily note down for this position the calculated angle on the sextant and the azimuth. If you can do that on this position, you could do it on this position, and you could do it on that position, or on this position, or any other position really. And furthermore, you can see that the whole calculations would be the same if the sun is over the Arabic countries and our position is in the Mediterranean, or the sun is over the Canaries and we are at the Azores, or the sun is south of the Azores and we are in North America. So it is all relative to our position and the sun's position. And that's why the sight reduction table is all about the local hour angle. The local hour angle means the difference in longitude between the sun and us. It's such a smart book, this sight reduction table. If you consider how many positions it's valid for and how thick the book is, you will be surprised that you can use it for so many places around the world. It gives the altitude that you should be reading off the sextant for each full degree of latitude and for each full degree of local hour angle. Before we do some exercises, let's just get some vocabulary done and some wordings and maybe some repetition. If we have a milestone and we have another milestone where it says London is 355 miles away, we know that the difference in distance between this milestone and that milestone is 1 mile. So that means that you take the differences between the two milestones. And now let's say that somebody has told you that if you sit on one certain milestone, you can look up in a book the angle and the direction of a certain body. I take a palm tree. So if you sit on this milestone, you should see the height of the coconut up there in a certain height, and the direction to the palm tree is approximately west. That's the azimuth. And this is the assumed position. So the vocabulary is that the assumed position is the position in which you can read off the height on the sextant HC and the azimuth out of the sight reduction table. If now you see the palm tree somewhat bigger than it is written in the book, so HC is, or HO, the observed altitude, is higher than the calculated one in the book, you are closer to the palm tree. And vice versa, if the observed altitude, HO, is smaller than the calculated HC, which is valid for the assumed position, you are further away. So the azimuth is the direction of the body, the palm tree in this case. HC is the pre-calculated height that you should see at the milestone 355 miles, which is the assumed position. And then when you are measuring a smaller angle, HO, you are further away. And then there you have the position line. That is the line which is 90 degrees to the azimuth. The azimuth is the direction of the palm tree. So somewhere along this red position line we are. And how far we are away from the other milestone, here we can say 1 mile, of course, but that is the intercept. So these words, these vocabulary, should be a little bit familiar to you by now. The most frequent mistake people do is that they make a dot, a position, where the intercept is ending, but it's not a position, it's not a dot, it's a line, it's a position line which is 90 degrees to the azimuth. To sum up, if you're still with me, in a nutshell, what is celestial navigation about? It is about you are proving you aren't where you think you are, and then the Astro gives you the exact measurement of your misjudgment. So that's what you're doing. You have assumed position, you know things about this assumed position, and then you can exactly say how much it differs to where you really are. So now we have come to a to-do list. The to-do list has 5 steps. And this is what we will do again and again and again and again when we do all the exercises and are sailing on the boat. Step 1, note and shoot. So what you need here is that you note your approximate position, you note down the course over ground, your log, the exact time, and you read off what the angle you are measuring on the sextant, that is the HS, and you do some corrections I mentioned, which are found in the template later, so you get the observed altitude HO. Step 2. Find the position of the sun. This you find in the nautical almanac. What you find in the nautical almanac is the sun's position, measured in declination, Greenich hour angle. You decide which assumed position you want to use in order to get a good local hour angle. What is a good local hour angle? It is a whole numbered local hour angle with a whole degree. No minutes, please. Why? Because in step 3, you use the sight reduction table, and here you will find the calculated angle which you should read on the assumed position and the azimuth Zn towards the sun. So how do you get that? You go into the book by using the local hour angle, and the book only exists for whole numbered degrees of local hour angle, so no minutes please. You use your latitude, a whole numbered latitude, which is your assumed position. You find in this book the calculated angle HC, and you get the azimuth. Okay, step 4, find the intercept. Because you have to compare the calculated angle, HC, with the observed angle, HO. And the HC you get from the sight reduction table, the HO you get from step number 1. So you take the difference in between that. That's the difference in the milestones, remember? So that's where you get the intercept. And depending on which number is higher, if your observed is bigger, you are closer, and if your observed angle is smaller, you're further away. Step number 5, draw everything into the chart. Draw your assumed position, and that's yellow there because you get it from the yellow from step 2. Draw in the chart from that assumed position a direction to the sun, which is the azimuth, Zn. The Zn is yellow because you find it from step 3. Then you should draw the intercept from the assumed position in direction of the azimuth, either away from the celestial body or towards the celestial body. That is also yellow because you get that answer on step 4. And where you end with your pencil, you take a 90 degrees and draw the position line. The position line is red because that is exactly what you want to find. So the whole exercise is to get the position line. Now you have step 1, step 2, step 3, step 4, step 5. And I have made a nice workflow, a very simple, but it doesn't look simple, but it is very simple when you then see it was very complete. And you just follow step by step a template. And this bespoke template comes here. Here it is. It has step 1, step 2, step 3, step 4, step 5. And to explain how this works, you use your template and do some exercises, and I will also do them for you as usual, so you can follow me how you can get your position line in the end.